This video is on derivatives of inverse functions. Two functions, f of x and g of x, are inverses of one another if they undo each other. So in other words, if f of g of x is equal to x and g of f of x is also equal to x. And in this case, we usually write f inverse x as f to the negative 1 of x. So this is our way of denoting the inverse. As a couple examples, f of x is x cubed, then f inverse of x is the cube root of x, because as we know, if we took, say, the cube root of x cubed, that would just give us x back. And similarly, if we took x to the third and then cube root, and if we took the cube root of x and then we took that to the third power, that would also just give us x. So those are inverse functions of one another. Similarly, g of x equals e to the x and g inverse of x equals natural log of x are inverses of one another. We know that e to the ln of x is equal to x, and the natural log of e to the x is equal to x. And as just one more example, log base 10 of x and 10 to the x are inverse functions of one another. So log base 10 of 10 to the x, that's saying what exponent do we need to raise 10 to get 10 to the x? Well, x is that exponent. And 10 to the log base 10 of x is also x. A function is one-to-one if it passes the horizontal line test. That is, can we draw a horizontal line anywhere across for any value of y, such that the function crosses the line at exactly one point? So this would be an example of failing the horizontal line test. So this is a no. And this is an example of passing the horizontal line test. So this is a yes for passing the horizontal line test. More formally, f of x is one-to-one if for any value y equals b, so at any point on the curve or any point y equals b, there is exactly one, or there is at most one, value a such that f of a is equal to b, or in this case, g of a equals b. There is at most one such point. Whereas here, for example, if this is maybe 4, then there are two such points, 2 and negative 2. And so this is not one-to-one, and this is yes, this is one-to-one. And why do we describe? That's because any function that is one-to-one has an inverse. And given the graph of a function, the graph of its inverse can be obtained by reflecting across the line y equals x. So if we reflect across this line y equals x, here, for example, is our g of x equals e to the x and g inverse of x equals natural log of x. If we just have a mirror there, reflecting across y equals x, we see the graph of g of x equals g inverse of x equals natural log of x. And similarly, over here, we've got f of x equals x cubed and f inverse of x equals the cube root of x. So for our original graph of x cubed, here it is. And when we reflect across the y-axis, we get the cube root of x, which is right here. And so basically the inverse function, one way of describing what it does, is that it switches the x and y values to y and x values. For some functions that are not one-to-one, we define their inverses on an interval that is one-to-one. So for example, y equals sine of x clearly is not one-to-one. This does not pass the horizontal line test, because if we look at any particular y value, there are multiple x values that give that same y value. So it's definitely not one-to-one, and that's just is a wave function that goes on forever in both directions. So instead, we choose a subinterval, and the subinterval that's generally chosen for sine to get its inverse is the interval from negative pi over 2 to positive pi over 2. So sine of x is one-to-one on that interval from negative pi over 2 to pi over 2. And we define the inverse of sine on that interval. So here is y inverse equals arcsine of x, or sine inverse of x. So some people or texts write the inverse of sine of x as arcsine of x. Others write it as sine to the negative 1 of x. Either is fine. Just note that there is a little bit of ambiguity here. You know, is this going to be inverse of sine of x, or is this going to be 1 over sine of x, because to the negative 1 power usually is 1 over something. So there's some ambiguity for trig functions, and that's why we often use arcsine, but using either form is fine. We are going to, you should always assume that if you see this, that it's really inverse of sine of x as opposed to 1 over sine of x. Now let's relate inverse functions to derivatives. Here is the derivatives of inverse functions theorem. If f of x is differentiable and its inverse is a function and f prime of x is non-zero over an interval, then the inverse is also differentiable over that interval, and the derivative with respect to x of the inverse of f is equal to 1 over f prime of f inverse of x. So here is the derivative of f inverse of x that is written in terms of the derivative of f. And here is a proof of that fact. Basically, this proof is going to use the chain rule. So first, we know that by a definition of inverse, f of f inverse of x is just x. Those two functions undo each other and give x back. Now we can take the derivative of both sides. So derivative with respect to x of f inverse of x is equal to the derivative with respect to x of x. And now we can use the chain rule on the left-hand side to get that the derivative of that is, outside function is f of x, so f prime of, leave the inside alone, f inverse of x, multiplied by the derivative of the inside, the derivative of f inverse of x, well, that's what we're trying to find. That is the derivative with respect to x of f inverse of x. And that's equal to, on the other side, derivative of x with respect to itself is just 1. So now we can solve for the piece we're interested in. We can just divide both sides by the remaining product. And so the derivative with respect to x of f inverse of x is 1 over f prime of f inverse of x. And so that is the end of our proof. All right, let's use that fact, the fact that the derivative with respect to x of f inverse of x is equal to 1 over f prime of f inverse of x, to prove a few derivative rules. So we have already seen that the derivative of natural log of x is 1 over x. Actually, we've used that derivative rule, but we haven't proved it up to this point. Now we are going to prove it using the inverse function, derivative of inverse function theorem. So we need the function that we want to find the derivative of. That's f inverse of x equals natural log of x. And the inverse of natural log of x, f inverse is just f of x, that's e to the x. So what else do we need? We also need f prime to be able to apply this theorem. So f prime of x, the derivative of e to the x, is just itself, is just e to the x. So now, according to the inverse function theorem, the derivative with respect to x of natural log of x is 1 over f prime is e to the something, f prime of f inverse of x, and that's natural log of x. So that is 1 over e to the natural log of x. Well, those are inverse functions, they just cancel each other out, so that's 1 over x. So we have shown that the derivative with respect to x of natural log of x is 1 over x. Now here's a new derivative rule for us, that the derivative of derivative with respect to x of log base a of x. So we're going to find that in general, and we're going to show that it's 1 over natural log of a times 1 over x. So we're going to show that that is true, and we're going to show it using the inverse function theorem. And so what do we need? We need, again, we want to find the derivative with respect to x of natural log of base a of x. So we're going to let f inverse of x be the thing we're interested in, log base a of x. We're going to then let f of x be the inverse of that. The inverse of log base a of x is a to the x, and therefore we'll also need f prime of x. The derivative of a to the x, we know, is natural log of a times a to the x. So we're going to use all three of those pieces. Now, that means that the derivative with respect to x of log base a of x is equal to 1 over, well, just in general, that's f prime of f inverse of x. So what is that in our situation? That's 1 over f prime is natural log of a times a to the x, but it's not just x, it's f prime of f inverse of x, so that's what's going to go up here where x would go. F inverse of x is log base a of x, and so now we can simplify that. That's 1 over natural log of a and a to the something and log base a of something cancel each other out. Those are inverse functions. So what we're left with is natural log of a times just x, or that's the same thing as 1 over natural log of a times 1 over x, and either way of writing it is fine. But that is the derivative with respect to x of log base a of x. All right, we're going to do one last derivative using the derivative of inverse function theorem. So we're going to do the derivative of sine inverse of x, or arc sine of x, and recall that that's defined just on the interval from negative pi over 2 to pi over 2. So f inverse of x, the thing we want to find the derivative of, is arc sine of x, or sine inverse of x. And that means that f of x is its inverse, which is just plain old sine of x, and f prime of x is the derivative of sine of x, which is cosine of x. So by the derivative of inverse functions theorem, the derivative of arc sine of x is equal to 1 over f prime, that's cosine of, and instead of x inside, we have f inverse of x inside, so arc sine of x. So that's technically the derivative, but we're going to do a little work to make it look more familiar or nicer. One thing that we know is that sine squared x plus cosine squared of x is equal to 1. Why is that true? Remember way back when we talked about trig functions and the unit circle and all that stuff, for the unit circle, cosine is the same thing as x, the side length of our triangle, because cosine is the adjacent over the hypotenuse when we're talking about a unit circle. So that's just x. And similarly, sine is just y, the opposite over the hypotenuse. And we know by the Pythagorean theorem that x squared plus y squared is equal to the length of the hypotenuse squared. So that's 1 squared. So sine squared x plus cosine squared x is equal to 1. That's a really useful trig formula to know. Okay, so we are going to apply that and rewrite cosine of x. So based on this, we could get cosine of x by itself. Cosine of x is equal to 1 minus sine squared of x, cosine squared of x is equal to 1 minus sine squared of x. And now taking the square root of both sides, cosine of x is equal to the square root of 1 minus sine squared x. All right, now let's see how we can apply that to our derivative. So we'll rewrite this as 1 over, instead of cosine x, we'll write it as the square root of 1 minus sine squared of arc sine x, all under a square root. And so this is the same thing as 1 over the square root of 1 minus sine of arc sine x times itself, sine arc sine x. And now sine and arc sine are inverses of each other. They undo each other. So this is 1 over the square root of 1 minus just x is sine of arc sine of x times x. And so that can be rewritten more simply as 1 over the square root of 1 minus x squared. So we've seen that the derivative with respect to x of sine inverse x or arc sine of x, either way, is equal to 1 over the square root of 1 minus x squared. And you can use similar techniques to find the derivatives of each inverse trig function. And again, each of these can be written either as, say, arc sine or arc cosine, or as cosine inverse of x. Can be written either way. But here are the derivatives of each of those inverse trig functions. One thing to notice is that they are the derivative of arc sine and the derivative of arc cosine are related. They're just negatives of one another. The derivative of arc secant and the derivative of arc cosecant are similarly negatives of each other, and the derivatives for arc tangent and arc cotangent, or tangent inverse and cotangent inverse, are also just negatives of each other. So that can be one thing to help. You really just need to memorize, say, the left-hand side, and then you've got the right-hand side for free.